So in the last session, we saw that one of the fundamental properties of a transaction is isolation. And to ensure this, the system must control the interaction among the various concurrent transactions that are running in the database at that point of time. And this is done through various concurrent control schemes. Okay. The first scheme is via lock-based protocols. We will also see some other protocols like the timestamp-based protocols later. We will then see how the granularity of the locks can affect the extent of concurrency allowed in the database, and how some issues of lock-based protocols like deadlocks are handled or prevented in the lock-based schemes. Okay, so let's look at the lock-based protocols first. So one way to ensure isolation is to require the data items be accessed in a mutually exclusive manner. That is, while one transaction is accessing a data item and wanting to write on it, no other transaction can modify that data item. Okay. The most common method used to implement this requirement is to allow a transaction to access a data item only if it is currently holding a lock on that data item. Okay. So a lock is a mechanism to control concurrent access to a data item. Okay. And data items can be locked in two modes. One is an exclusive mode where a data item can be both read as well as written when it has an exclusive mode on the database item. So the X mode or the exclusive mode, this lock is requested using a lock X instruction. Okay. The next mode is the shared mode. So when a mode is a shared mode, the data item can only be read by that transaction. Okay, so S lock is requested using the lock S instruction. Okay. So we require that every transaction request a lock in an appropriate mode on the data item queue with which it wants. Okay. Depends on the types of operations that will perform on queue. So if it wants to do a read, it will ask for a shared mode lock. If it wants to do a write, it will ask for an exclusive mode lock. Okay. So the transaction makes the request to a to the concurrency control manager, and the transaction can proceed with the operation only after the concurrency control manager grants the lock to the transaction. Okay. The way in which it can grant the lock is normally represented by a matrix, which we have shown over here. Okay. So given a set of lock modes, we can define what is called as a compatibility function, which represents the matrix. Okay. Suppose that the transaction Ti requests a lock of mode A on an item Q. Okay. On which transaction Tj, obviously Ti is not equal to Tj, currently holds a lock of mode B. Okay. If transaction Ti can be granted a lock on the item Q immediately, in spite of the presence of the mode B lock, then we say mode A is compatible with mode B. Okay. So an element of the compatibility matrix A, B of the matrix has a value true if and only if mode A is compatible with mode B. Okay. So given this, we have the two shared modes are the only ones that are compatible. The others are false. Okay. So the shared mode is compatible with shared mode, but obviously it is not compatible with exclusive mode. Okay. So at any time, several shared mode locks can be held simultaneously by different transactions on a particular data item. Okay. A subsequent exclusive mode lock request has to wait until the currently held shared mode locks are released. Okay. A transaction requests a shared mode, a lock of shared mode on data item Q by executing the lock SQ instruction. Okay, so that is the lock S for shared mode, and Q is the data item which it wants. Okay. Similarly, a transaction requests an exclusive lock through the lock XQ instruction. Okay. A transaction can then unlock a data item by the unlock Q instruction. Okay. To access a data item, transaction Ti must first lock that item. If the data item is already locked by another transaction in an incompatible mode, the concurrency control manager will not grant the lock until all incompatible locks held by other transactions have been released. For this, Ti may have to wait until all incompatible locks held by other transactions have been released. Okay, so that is how the protocol works for locks. Okay, so a point to note, a transaction may be granted a lock in an item if the requested lock is compatible with the locks already held on the item by other transactions. Okay, so the matrix will allow any number of transactions to hold shared locks on an item. But if any transaction holds an exclusive lock on the item, no other transaction may hold any lock on the item, and we said the transaction may need to wait. Okay. So all lock and unlock requests are handled by the lock manager. Okay. And the lock manager has a data structure which we will call as a lock table that represents all the items, or that contains all the items for which the transactions have requested locks, and which are the transactions that are holding those items. Okay. So the lock table entry basically has the number of transactions currently holding a lock, the type of lock held, whether it's shared or exclusive, and a pointer to the queue of lock requests. So we can visualize it to be something like this. Okay. Another point to note is all locking and unlocking have to be atomic operations. That means the entire operation cannot be interruptible. Okay, that is, a lock cannot be, whilst locking it, it cannot be interrupted, and whilst unlocking it also, the sequence of instructions during that cannot be interrupted. Okay, so if we look at this figure, it basically shows an example of a lock table, and the darker blocks represented those locks which have been granted to those transactions. So it represents the transaction that has been granted a lock, and a lighter block shows transactions that are waiting for locks. Okay, so if we look at this, the table contains locks for 5 different data items, which we can look at as I7, I912, I4, I44. Okay, and the lock table basically uses overflow chaining. There is a linked list of data items for each entry in the lock table. Okay, there's also a list of transactions that have been granted locks or are waiting for locks for each of the data items. For example, if we look at transaction T23, it has been granted a lock for the item I9112, and it is waiting for a lock for item I4. Okay. The lock table should also maintain an index on transaction identifiers so that it is possible to determine efficiently the set of locks which are held by an individual transaction. That is not represented in this lock manager. Okay, this lock manager is only showing you the lock tables, not the identifiers or not the items for every transaction. Okay, so the lock manager basically processes requests in the following way. When a lock request message arrives, it adds a record to the end of the linked list for that particular data item if the linked list is already present. If the linked list is not present, it creates a new linked list containing only the record for that particular request. Okay. It always grants a lock request on a data item that is not currently locked. But if the transaction requests a lock on an item on which a lock is currently held, the lock manager grants the request only if it is compatible with the locks that are currently held. And all earlier requests have been granted already. Okay. Otherwise, the request has to wait. When the lock manager receives an unlock message from a transaction, it deletes the record for that data item in the linked list corresponding to that transaction. Okay. It then tests the record that follows it to see if that request can now be granted. If it can, the lock manager grants that request and processes the record following it, if there are any more, in a similar manner. Okay. If a transaction aborts, the lock manager deletes any waiting request made by the transaction. Okay. Once the database system has taken appropriate actions to undo the transaction, it releases all the locks held by the aborted transaction. Notice that this algorithm that is followed guarantees freedom from starvation for lock requests, okay, because there is a linked list and all the requests are serviced in that particular queuing order, okay. We just saw that to access a data item, a transaction must first lock that item. If the data item is already locked by another transaction in an incompatible mode, then the concurrency control manager will not grant the lock until all incompatible modes held by other transactions have been released. Okay. The transaction may have to wait until all incompatible locks held by other transactions are released. But we saw that because of the linked list method of storage of the transactions, there is not going to be any starvation. Okay. So here is an example of a transaction T2 which performs locking. So it locks in shareable mode a data item A. It reads the data item, it unlocks it. Then it locks in shareable mode a data item B. It reads it, unlocks it, and then maybe displays the sum of A plus B. Okay. Now, the question is this mechanism sufficient? We will see in a little while why it is not necessarily desirable for a transaction to unlock a data item immediately after its final access of the data item. Okay. And the reason for it is we will see that serializability of this is not, of the transactions are not ensured, because what happens is when it unlocks data item at this point over here, if there is another transaction that takes in the data item and does a read maybe on A and maybe does an update on A, and then before transaction T2 that takes a lock on the item B, the next transaction that had come in also does some updates on B. Okay. We saw that in a situation like this, when there is an intermediate reading over here at this point of time, if some other transaction, say T1, does a write on A and a write on B, okay, it does this, and then this next transaction takes over, okay. We saw that we could end up in an inconsistent state because this kind of transactions, this kind of interleaving of instructions of transactions do not give you serializability. Okay, there will be a conflict unserializable schedule. Okay, we cannot have a serial schedule of such kind of transactions. Okay, so that means we have an issue over here. So locking as above, that is shown over here, is not sufficient to guarantee serializability. Okay, so if A and B get updated in between the read of A and B, the displayed sum would end up giving you a wrong answer. Okay, so a locking protocol needs to have a set of rules that decides when the locks need to be unlocked. Okay, so we will look at this in a little while. But before that, we will look at some issues that can take place. Okay, so these locking protocols, because they ensure some rules on the way in which locks can be done, would reduce the amount of possible schedules that are allowable in the system. Okay, so here's the example that we have over here. Transaction T1 and T2 are executing concurrently. Here we're looking at the fact that transaction T1 has taken an exclusive lock on the data item A, done a writing and unlocked it. Okay, transaction T2 has been executing next in the middle. It takes on the lock. Since this is unlocked, this lock could be granted. Okay, so it reads the item A, updates it, unlocks A, reads the item B, updates it, unlocks B. Transaction T1 now takes over again, locks B in exclusive mode, does its write and unlock, right? So what happens is we have a problem over here because the transaction over here T2 basically has done a read of the data item A of T1 over here, but of B it has read from the database. And transaction T1 has read A from the database and B of the updated value of T2. So we end up having inconsistency, and we've seen such schedules prior. Okay, and we saw that these schedules are not serializable. Okay, so that's the problem that we have. The schedule is not serializable. So what if we ask ourselves this question, what should be done to ensure serializability? We just realized that unlocking the data item too early. Because we unlocked A over here, this transaction T2 could take A. So the question is, should we unlock A at this point of time, or should we delay the unlocking? So obviously we need to delay the unlocking because we don't want T2 to take A and do some modifications until T1 has kind of not wanting to use any other locks on the transactions. So the question is, how long do we delay the unlocking of the database item that we have taken in a exclusive mode previously? Okay, so that is the issue, or that is what needs to be looked at, and there are protocols that decide when this can be done. It's one of the protocols is a two-phase locking protocol, so we will see this in the next session. Okay, but for now we know that we need to follow a protocol and delay the lock release. So we will see when the locks can be unlocked later. Okay. So here's a point to note. At some point in the life of every transaction, it should hold all the needed locks. Okay. Because once it's holding all the needed locks, then we know that no other transaction can interfere with this currently executing transaction that holds these locks on it. Okay. So any other transaction must have got its locks on the conflicting items either before or after this particular transaction. Okay. So that would basically ensure conflict serializable schedules. Okay. Let's look at some more issues before we look at the two-phase locking protocols and the other kinds of protocols that are. Okay. So here we have a transaction T3 and a transaction T4. T3 has taken a lock, exclusive mode lock on B. It does its modification and it writes B. Okay. Notice that it has not unlocked B here. But another transaction T4 has taken a lock on A in shareable mode, taken a lock on B in shareable mode. Okay. It was granted the lock on B because this particular transaction over here, let me take that back. It can ask for a lock in shareable mode on B, but it will not be granted the lock on B because this current transaction T3 is holding a exclusive lock on the data item B. Okay. So this transaction T4 now is waiting because there's an incompatible lock for the transaction item B that it wants. Okay. So it's waiting at this point of time. Okay. So here, this particular transaction is waiting, okay, for the lock. Now, this transaction has continued and it continues its execution. It now wants a lock on the data item A, but not a shared lock. It wants an exclusive lock on A because maybe it wants to do a write. So what tends to happen over here? Because there is a lock S over here for T4 on the data item A, this becomes incompatible and this particular transaction is waiting at this point of time. Okay. Now, if you look at this, transaction T4 is waiting for the lock on B and transaction T3 is waiting for the lock on A. And these locks will never be released because they are both waiting on each other, right? So this is a deadlock. That means the protocol that we're looking at first, although we have not unlocked it, can cause a deadlock. Okay, so we need to see this also and see how this issue is basically handled. Okay. So neither T3 nor T4 can make any progress. Executing lock S B causes T4 to wait for T3 to release its lock on B, while executing lock X on A causes T3 to wait for T4 to release its lock on A. Okay, so we end up in a situation called deadlock. So we will see how deadlocks are prevented or also handled in later session. Okay, so the potential for deadlock exists in most locking protocols. Starvation is also possible if concurrency control manager is badly designed. But we said that because of the linked list method and the fact that it's a queue, the locks can be given to the transactions in the queue. So there is no starvation. Okay. So when can starvation happen? A transaction may be waiting for an X lock on an item while a sequence of other transactions request and are granted an S lock on the same item. So this kind of a starvation is possible also. Okay. So then what the lock manager will need to do is keep a bound on the number of times a particular transaction can get a shared lock when there is a waiting transaction for a incompatible lock mode. Okay. So this is a consequence of starvation. When we decide who's the victim, you'll find that the same transaction is repeatedly rolled back because it wants the lock in an incompatible mode and doesn't get that lock. Okay. So we will look at the two-phase locking protocol and the modifications to them to see that some of the issues that we have just looked at have been removed in the next session. Okay.